Good morning, dear students. Hope you're all safe and fine. Welcome you all to the video today on ARM pipelining. We have just seen the basics of pipelining in one of our classes earlier, but still I would like to tell you some in-depth details about ARM 7 pipelining in this video. So hope you have seen yesterday's video on programmer's model, and I hope you're clear with that because that is a very important topic in ARM 7. That is understanding the 37 registers of ARM 7. So ARM, one of the very powerful feature in ARM is this pipelining concept. So that is the reason why ARM is used in many appliances and devices, is because it has got a very strong pipeline implemented. So let us see what is the pipeline concept. So coming to the today's video, we will be discussing three things. One, what is the advantage of having pipeline over a processor which do not have a pipeline? Okay, so that will be the first topic. Second, how pipelining is implemented, or how many stages are there in ARM 7, and then how it is implemented. And third, we will be discussing on the hazards. Okay, so pipeline has got some problems and issues which has to be sorted out. So they are known as hazards. So let's see what are the hazards and how these hazards occur. Okay, and so that is the agenda for this video. Now coming to the before going into advantage of pipeline, let me just we know that, but still we'll just quickly review. Whenever an instruction has to be executed, this is the procedure that happens. Be it a RISC processor or be it a CISC processor, this is how the process happens. So first we start the first instruction. So when we start the first instruction, we fetch the instruction, okay, and then we decode the instruction and then we execute. And then we check whether there is a next instruction or not. If there is a next instruction, then it continues in a loop. Okay, we fetch the next instruction, decode, and then execute and go on. So this is what is the normal procedure of how an instruction is executed in a processor. Now, if we compare a processor which do not have a pipeline with a processor which has a pipeline, let's see that, here you can see that, let's say that there are totally 4 instructions. Okay, we are taking a very simple example. Totally a program has got only 4 instructions. It's a small program. And let's say that the number of stages that it takes to execute every instruction will be 3 stages. So every instruction has to undergo 3 stages for it to be executed. So let's see, the first instruction is fetched in clock cycle 1. The first instruction is decoded in clock cycle 2. The first instruction is executed in clock cycle 3. So for one instruction to be completely fetched, decoded and executed, it takes 3 clock cycles. Similarly, for the second instruction, it is 4, 5, 6. For the third instruction, it is 7, 8, 9. For the fourth instruction, it is 10, 11, and 12. So completely, for 4 instructions to be fetched, decoded, and executed, assuming that all stages take only 1 clock cycle, the total time taken for 4 instructions to be executed is 12 clock cycle. Is that clear? So this is for a processor which do not have a pipeline. Now coming to the ARM processor which has got pipeline, you can see here same 4 number of instructions and same all instructions are executed in 3 stages. You can see that the first instruction is fetched in clock cycle 1, decoded in clock cycle 2 and executed in clock cycle 3. But since there is a pipeline, in clock cycle 2, not only the first instruction is decoded, but simultaneously the second instruction is also fetched. Okay, so when first is decoded, the second is fetched. Similarly, in the third clock cycle, when first is executed, the second moves to decode phase and the third instruction is fetched here. Okay, so what happens is, just observe the style here. When it is a processor without pipeline, the style of instruction execution will be fetch, decode, execute. Fetch, decode, execute. Fetch, decode, execute. So it goes like this. But whereas when there is a processor with pipeline, it is fetch, decode, execute for the first instruction. Then onwards, every clock cycle it is execute, execute, execute. Okay, so it is fetch, decode, execute, 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 execute. So once one instruction undergoes, three stages, all other instruction will only take one clock cycle to just complete its execution. So that is one of the major advantage of going for a pipeline processor. So here you can see the total number of clock cycles taken to execute the same four instructions, which undergoes three stages of execution, is 6 clock cycles. So now you would tell me what is the time saved when it is a processor without pipeline and processor with pipeline. Yeah, are you telling that it is 50% time saved? May not be true, because the number of instructions is less, it is just only 4 instructions, so it is looking like as if it is 50% of time is saved. But imagine there is a big program which has got 100 instructions. What is the time taken for it to be implemented in a processor without pipeline? 100 into 3 clock cycles, so which is equal to 300 clock cycles if it is executed without pipeline. Now, if it is executed with pipeline, for the first instruction alone, it will take 3 clock cycles, right? Fetch, decode, and execute. From then onwards, for the remaining 99 instructions, it will take only 99 clock cycles, because execute, execute, execute. So 99 plus 3, 100, 101, 102. So total number of clock cycles taken will be only 102 with pipeline. But whereas without pipeline, the total number of clock cycles taken was 300. Are you getting the difference now? So more the number of instructions, more will be the time saved due to pipeline concept. So that is the beauty. So almost the time saved due to pipeline would be 1/3 and not 50%. Okay, so that is the biggest advantage of having pipeline, and that is the reason why ARM processors are really fast compared to any other CISC processor. Now, coming to the stages of pipeline, we already have seen this stages of execution of an instruction. Same thing is converted into stages of pipeline. ARM 7 has a 3-stage pipeline. Okay, so higher versions of ARM have 5-stage, 9-stage, 11-stage, and so on. But we are seeing the basic of ARM 7. ARM 7 has got 3 stages. First stage is fetch, second is decode, and the third stage is execute. Now coming to how is it possible? Okay, what are the features in ARMs that make this an ARM processor that makes this pipeline perfectly possible? Let's see one by one. So the 3 phases are fetch, decode, and execute. So what all is there in fetch that helps it to be completed exactly in 1 clock cycle? Can you please recall? We have already discussed this in our earlier videos. So what are all the features in ARM that helps all instructions to be fetched exactly in 1 clock cycle? Yes, the answer is, we already know, all instructions in ARM are of same size, which is 32-bit when it is a normal execution and 16-bit when it is a thumb instruction, right? Thumb state. And all your data bus is exactly 32 bits. So when you fetch, exactly you fit it into your data bus, and then it is easily fetched from the data bus. And more important is, all instructions are aligned. Okay, when they are saved in the memory, they are not just like that saved. They are just aligned and saved. I hope you understand what is aligned. So aligned means one instruction is 32 bits. 32 bits will take 4 bytes, right? So what happens is, these 4 bytes are saved in 4 locations. Location 0, location 1, location 2, and location 3. So when I want that instruction, just in one go, I will be able to take it from the 4 different locations. So I will get all the 32 bits in one go. So that is the best part of ARM processor. The instructions are stored in aligned memory. Okay, and this is the reason why you are able to fetch the instruction, almost all instructions in 1 clock cycle. Okay, so whenever you are asked to write about pipelining concept of ARM 7, you should not only say that it has got 3 stages and all that, you should also mention what are the features in ARM 7 that helps the perfect implementation of pipeline. So this is regarding the fetch phase. Now coming to decode phase, what are the features in ARM that makes it a perfect uh, pipeline is number one, all instructions and addressing modes are very simple. We have seen that in the first video, which is about difference between RISC and CISC. So here all the instructions are very simple, okay, and also the addressing modes are also very simple. So because of this, the decoding phase becomes, very easy and simple. Okay, and there are actually two ways of decoding. One is hardwired decoding, and another is decoding by using a software. The one that is followed in ARM 7 is hardwired decoding. That is, decoding is done using some hardwares, and always hardwired decoding is faster compared to decoding using a software. And that is one of the another reason why decoding can be completed in exactly one clock cycle. Now, the third one is what makes execution to complete in one clock cycle is, we know that all arithmetic and logic operations are completely register based. So all instructions, all operands or all data that are required for both arithmetic and logic operations are stored in registers, and we don't access the memory for getting any operand, right? So that is one of the major advantage of ARM. And all registers are 32-bit, so easily we can take the data, put the data back and all that. So all registers are 32-bit, and your ALU also is exactly 32-bit. So this uniformity, you can see that even in this slide, you can see here your instructions are 32, your data bus is 32, your registers are 32, your ALU is 32. So this is one of the major advantage of ARM, that is you have a uniformity, and of course all your buses are also 32 bits, that is your address bus, data bus, and so on. So because of all these features, it is possible that, it is highly possible that ARM can have a perfect pipelining concept. But everything should have, another side, like there should be a flip side for every concept. So even pipelining may have a flip side, right? And let's see a video. Next is a video. Just watch this video. Yes. So what do you understand in this video is, even if one instruction, okay, fails to either fetch in one clock cycle or decode in one clock cycle or execute in one clock cycle, the effect will go through to the entire pipeline. Okay, even if one instruction, there is a delay either in fetching or decoding or execution, that delay continues throughout the pipeline, and the entire pipeline would be, stalled or would be paused. Okay, it would not follow its regular time. So that is what we call as hazards. Okay, so these hazards are possible in any pipeline processor. So any condition that causes a pipeline to stall. What do you mean by stall? Is pause or delay. So whenever there is a delay, instead of pipelining complete, every instruction should be executed uh, in just three clock cycles. If there is one instruction also, if there is a delay, then it causes a stall. So that condition in any processor that executes using pipeline is called as a hazard. And there are three types of hazards. The first hazard is called the structural hazard. We'll be just seeing what it is. Okay, actually every type has got some solutions and all that. We are not going deep into it. We're just going to see what are the types of hazards and how the hazard occurs. So first hazard is called the structural hazard. The second hazard is data hazard, and the third is the control hazard. So let's see one by one how the hazard occurs. Now, first is structural hazard. As a name itself, specifies, whenever two or more instructions, they try to use the same physical structure. It may be a memory, it may be ALU unit, or it may be the ports of your processor, whatever. Okay, when two instructions try to use the same resource or same structural or physical resource of your processor, then there may be a conflict between the instructions. Okay, so that causes an issue. and that is known as a structural hazard. So here you can see that in clock cycle 3, this is clock cycle 1, clock cycle 2 and clock cycle 3. So clock cycle 3 is the first place where first instruction is executed, second is decoded and third is fetched. So during fetch you may have to use the memory. During execution also, suppose you have to store the result back into memory. Usually that doesn't happen. Most of the results are stored back only in the registers, but in case you have to store the result back into memory, at that time for fetching the third instruction also you may have to refer to the same memory. So there may be a memory conflict issue, right? So instruction 1 is also trying to use the memory to store its result. Meanwhile, instruction 3 is also using the memory to fetch. And we know that ARM7 is a von Neumann architecture, which is do not have two memories. All programs and data are stored in the same single memory. So in that case, there may be a conflict that would arise between instruction 1 and instruction 3. And this conflict is due to structural or physical, the availability of the processor. And this hazard is known as the structural hazard. Okay, that is the first hazard that is possible in a pipeline. Coming to the second hazard, before that, just look at this picture. Now, come on, tell me how many colors are there in this picture? There are only two colors, that is the black and the blue color. Now, if I just, two people are drawing this picture simultaneously, and person one has got both blue and black color pen or pencil or whatever, but the second person has got only a blue pen or a pencil but does not have a black. So what happens? The first person, since he has both, he will have to completely finish this diagram and then only share the black color pen or pencil with the second person. So the second person will have to wait for the first person to completely finish the drawing and then get the black color from him, and then he has to complete. Now this condition also happens in processors. Okay, and we call this condition as data dependency. I am repeating it. This condition is known as data dependency. So let's see what is this data dependency in detail. Now let us take these two instructions. Add R1, R2. What happens in this first instruction? The first data from R1 is taken. Second data is available in R2 register, which is also taken, added, and the result is stored back in R1 register, right? So this is what happens in the first instruction. Now coming to the second instruction, it is an AND operation, logical operation. So you are ANDing the two values. The first value is available in R1 register, the second value is available in R0 register. So you are taking the two values from R0 and R1, performing logical AND operation and storing the result in R0. Now this is similar to the analogy that I explained to you in the previous slide, black and blue color. So here you can see this is the black color and this is the blue color. Now this person has got both the data, so it is just adding and then producing the result in R1. But here the second person requires this updated R1, that is R1 after adding it with R2. Got it? So this AND operation has to be performed on the updated R1 register. So it has to wait for the first instruction to complete it, store the result back in R1, then only this can start its processing. So this is what we call in computer terminology as data dependency. So you can see that here the first instruction, the instruction here is executed here, and instruction, and the result has to be stored back into R1. And the second is the logical AND instruction, it has to be executed. So when it is executed, the result has to be updated in R1. If it is not correctly updated in R1, then the second instruction execution may give a wrong result. If it is going to take a value that is before updation, okay, and it may give a wrong result. So this is what we call it as data dependency. And this data dependency may cause a stall in the pipeline. Okay, so this is known as data hazard. So data hazard occurs when instructions that exhibit data dependence modify the data in different stages of the pipeline. You're clear? So here you will be getting the result of R1 plus R2. Okay, and it is stored in R1. You have to take the updated R1 value here. You cannot take the old value of R1. Okay, so it has to wait for the previous instruction to exactly complete and then store the result, only then it can take. So whenever there is a data dependency, okay, there may be a possibility for a hazard, and that hazard is called as data hazard. So here the data here means data dependency. Now just look at this instruction, add R1 comma R2 and R4 comma R3. So here R1 and R2 is added, stored in R1. R3 and R4 are logically ANDed and stored in R4. So here this is an example of two instructions which do not have data dependency. Hope it's clear now. So here this is a set of instructions which has data dependency, and this is a set of instructions which do not have data dependency. So when there is no data dependency, there is no possibility of data hazard. But whenever there is data dependency, there is a possibility of data hazard. Yeah. The third hazard is actually one of the hazard that mostly happens compared to structural or data. Control hazard is something that is more possible to happen even in ARM7 processor, because all processors have something known as branch instructions, right? So whenever there is a branch instruction, there is a possibility of an hazard, and that hazard is known as control hazard. In some textbooks, it is also referred to as branch hazard. Okay, so there are two terminologies for it. So whenever there is a branch instruction, a hazard occurs, and that is due to decision making of the branch, and that hazard is known as control hazard. Now let's see what is this control hazard. Now the first instruction is fetched, it is decoded, and it is executed. Only when I execute, I understand that it is a branch instruction. Are you getting it? Only when I execute, I understand that it is a branch instruction. We all know that whenever we have also done it in our lab and all that. Whenever it is a branch instruction, we do not have to fetch the next instruction immediately. Instead, we have to jump. Okay, say suppose the branch instruction says that you have to jump to the fourth instruction. So which means what? You need not have fetched the second, you need not have decoded the second, and you need not have fetched the third. So these three things that we have done is of no use now, because E1 says it is a branch. So branch means what? Say suppose it is a branch from first instruction to fourth instruction. So after E1, here actually you should have fetched the fourth instruction. Am I right? But we have wrongly fetched the second, decoded the second, and also we have fetched the third. So this, what you have to do, remove this second and third instruction from the pipeline. Okay, so that is, you have to take off those two instructions, and then fresh you have to fetch the fourth instruction. Are you getting it? If the branch is from first to fourth, fresh you have to fetch the fourth instruction. So naturally this will cause a delay. Okay, and this delay, the reason for this delay is not because of unavailability of physical structure, or not because of data dependency, but it is because of occurrence of a branch instruction. Okay, and that is the third hazard, that is known as the control hazard. So these are the three hazards that occurs in generally in a pipeline. So they are a structural hazard, which is due to presence of which is due to two instructions trying to use the same physical structure. It may be a memory, it may be ALU, it may be input output ports, or whatever, or maybe even the same register, okay, by mistake if it is happening. Second is a hazard that occurs due to dependency of data. So whenever one instruction output has to be passed on as an input for the second instruction immediately, okay, then that may cause stall in the pipeline, and that is the second hazard known as data hazard. And the third hazard is whenever there is a branch instruction, there is a high possibility that you would have fetched the wrong instructions in the pipeline instead of taking the jump instruction, that is the branch instruction. So that causes kind of stall in the pipeline, and that is known as the control hazard. Clear? So these are the three hazards that can occur in a pipeline processor that would be possible in ARM7 also. Just a small review question to all of you. Please watch this question and message me the correct answer for this question. In the ARM7 pipeline, which of the following scenarios of data dependency will always result in a pipeline stall? There is no chance that there won't be a stall. Always there will be a stall. And that is due to data hazard without any instruction scheduling. Actually, there is something called prefetching. Prefetching means, we have seen that only one instruction will be prefetched, right? Instead, you have a buffer and then you prefetch 4 or 5 instructions and keep them ready. And then, you whenever there is a branch hazard, you take that from the buffer and then use it. But that concept is not available in ARM7. Higher versions of ARM it is available, but in ARM7, instruction scheduling and prefetching is not, it is not very extensively available. So now tell me the answer. Is it an AND instruction followed by a subtract instruction, a store instruction followed by a load instruction, a load instruction followed by an add instruction, or an add instruction followed by a AND instruction? Okay, so the 4 possibilities. Which possibility will surely always cause data dependency? Okay, and that data dependency will also cause data hazard. Please give this answer as a comment after you watch the video. So that's it, my dear students, for today's video. So today we have seen about the pipeline concept of ARM7 and what are the features in ARM7 that helps in perfect implementation of pipeline. And we have also seen what is the hazards and what is the reason for these hazards to occur. So thank you very much for listening to this video, and all of you enjoy your time with your family. Okay, this is the best time that God has given for all of us to spend with our loved ones. Okay, so enjoy each and every minute with your family, and all the best.